Hi everybody. In this transformer example, I'm going to go through one of the questions from the class notes, and we'll talk a little bit about transformers through this video. The key thing to remember is also that I'm not going to repeat the whole lecture notes in this video. Because I want you to read through the lecture notes anyway, and then I don't want you to have to spend double the time then watching me say everything that you've read. But we'll touch on some key points, and you should make sure, if you haven't done it yet, that you go back to these notes in the lecture and actually read through these notes. So we're talking about transformers, and I'm going to draw the schematic symbol for a transformer here. So I've got a primary coil. This is not a very good drawing. And a secondary coil. Okay, and the number of turns on these coils, I have NP on the primary and NS on the secondary. So the number of turns on these coils are different, could be different between the primary and secondary. They could be the same. If the number of coils is the same, this turns ratio is the same, we call it an isolating transformer. But quite often they're different because we either want to step up the voltage or step down the voltage. And the thing to remember here is that that there's no physical connection between these two coils. They're inductively coupled. Okay, so there's no physical connection, they're inductively coupled. And so this transformer is only going to respond to AC signals. It would not respond to a DC input. So I'm going to put an AC input here on the primary side. So I'm going to say this is VP with a positive reference there. And I'm going to put a load resistor, and I can draw a resistor, a load resistor also like a little box like this. So this is going to be my load resistor on the secondary, and I'm going to say that VS is the voltage across there. Now I also have a current through the secondary and a current through the primary. Okay, and so this turns ratio, the relationship between the number of turns on the primary and secondary, that becomes very important, right? So the turns ratio, as we write it, this little n, is the number on the secondary over the number on the primary. Okay, and so we know then that this is also the ratio of VS over VP, and the inverse of this, and this ratio is also IP over IS. So notice that the current ratio and the voltage ratio are actually swapped, and that is appropriate here. So looking at these equations, we know that the voltage on the secondary is equal to the voltage on the primary times NS over NP, which is VP times this turns ratio. And so you can see if NS is less than NP, we're going to step down and VS is going to be smaller than VP. But if VS goes down, IS goes up because the total power remains the same. And so that's a really important concept here, and that's why this ratio, IP is on the top, whereas this ratio, it's VS that's on the top. Okay, so the power from one side to the other remains the same, so if the voltage goes down, the current will go up and vice versa. Okay, so we're doing a little example here. So this is example 3 from the class notes that are posted on transformer, and it says a transformer has 200 turns of wire on the primary. So I'm going to write that down. So this is example 3 from the notes. So it's saying to me that NP is 200, and it says 20 turns of wire on the secondary, so NS is 20. And the primary is connected to 120 volts AC, so I know VP is 120 volts AC. I know that the load resistor, RL, is 100 ohms connected to the secondary. And the question is, what is IP and what is IS? These are the questions. Okay, so what are the currents? So going back and looking at this example, we've got 100 ohms. This would now be our 100 ohm resistor. NP is 200, NS is 20, this is 120 volts RMS, and we want to find this current and this current. Okay, so I'm going to find my turns ratio. So my turns ratio is NS over NP, so this is going to be 20 over 200, which is 1 over 10. And then my VS is going to be equal to this turns ratio times VP, so I'm going to have 1/10 of 120 volts AC. And AC, I mean, that's RMS, right? So this is going to be 12 volts RMS, okay, volts AC. And so I've got 12 volts on the secondary. So that means this is 12 volts. Now, if I know that this VS is 12 volts and this resistor is 100 ohms, then I can use Ohm's law to find this current, right? Because I know that V equals IR. This current is also what is flowing through this resistor. I know the voltage now across this resistor. So I can find I secondary as 12. Well, actually, I should always write out the full equation before putting in values. And actually, that's something that is super helpful when you're crunching equations. Keep the variables as far as you can in the process of solving your equation before you sub in actual values. Otherwise, you might have to carry long numbers and decimal places through multiple steps, and you might miss simple cancellations that can happen, and it's just more onerous. So I leave the variables in, and then only at the end do I sub in these values, 100 ohms, and so this is 120 milliamps, or 0.12 amps. And then if I want to go back and find IP, I know that, I'll write that off to the side, I know that NS, or that, this N turns ratio is IP over IS. And so if I want to find IP, that's going to be IS times this ratio, which is going to be 120 milliamps divided by 10 equals 12 milliamps. So what we saw here was that the turns ratio was 1 over 10, so this means this was a step down transformer when we're talking about the voltage, which we are, so we call it a step down. And indeed we saw the voltage dropped from 120 volts AC at the primary to only 12 at the secondary, but that meant that the secondary current is higher than the primary current, because the power from one side to the other of the transformer has to remain the same. So you can see that VPIP is the same as VSIS. Another important thing that we can talk about with the transformer, and I'll just draw a little transformer schematic here again, is a couple of things. So you'll see on some transformer symbols or on transformers themselves a little dot, primary and secondary. And what that is telling you is that if you measure VP and VS with the scope, and you put the scope leads the same way so that the red lead is where the dots are, then VS and VP and VS are going to be in phase. So they might have different, I'm not drawing that very well, they might have different amplitudes, right? Because they might have stepped up or stepped down, but they're going to be in phase with each other like so. Okay, but if you reverse the scope leads and on the secondary you put the black where the dot is instead, you're going to find that secondary voltage now flips and is 180 degrees out of phase. Okay, and where that comes important is if you have a transformer that has multiple secondaries with the dots here, you will get a different output whether you connect, say you wanted to connect these two secondaries together. If you connect them like this, you're going to get a different result than if you had connected like this and taken your output here and here, okay? Because where that dot is referenced to will decide whether that waveform combines additively or subtractively in a subtractive way. Okay, so that becomes important. The other thing I can do is to test a transformer measuring its windings. So I'm just going to erase those connections. So I have primary and secondary here, primary, and I have secondary 1 and secondary 2. Now, to test the transformer in general just with an ohm meter, I can measure the resistance between, say, leads 1 and 2 here, and I should get some resistance reading. Okay, if I get 0, that's a problem, and it means there's something wrong there. But it should be some low resistance value. And between leads 3 and 4 on this secondary, same thing, I should get a low resistance value. And 5 and 6, same thing, I should get a low resistance value. But remember that these coils are not physically connected, right? They're inductively coupled. So, but they're not physically connected, which means if I measure between resistance between 4 and 5, that should be an open circuit, right? Because they're not actually connected. So so if I did get a reading there, that would mean that something had shorted internally, and that would be a mistake. Same if I wanted to measure resistance between 1 and 3, right? They're not connected either, so I shouldn't get I should get an open circuit resistance reading there, or infinity ohms, to indicate that they're open circuit, however your meter displays that, because they're not actually touching. They're inductively coupled, but electrically they're isolated. So so if you're looking at the leads you know, between the two leads of the primary, you should get a small ohmmeter reading. But if you're looking between the primary and the secondary, or two different secondaries, you should get the open circuit reading. Okay, if you get 0 or a small resistance in that case, then you know that something's wrong. So give the questions on the worksheet, the transformer worksheet, a try, and let me know in the live session if you have any questions about that worksheet, but that will get you practicing some of the concepts that we talked about here. Okay.